All right, welcome again, everyone. So this is going to be, somebody requested this paper. So I'm going to go ahead and start working it out. I'm not sure if I'll be able to finish all of what, the paper holds, because I mean sometimes it takes a little while to to answer all these questions and to explain and all of that. But it's the 2019 Unit 2 past paper question. I mean it's a very I would say not difficult, but it can pull your mind to a certain extent when you look at the questions and all that. But it's all about applying small principles as we go along. Now, one of the things you must understand, ladies and gentlemen, right, as you prepare for your exams, there are certain definitions that they will normally start out with on the exam papers, right? So you can expect your definitions to come from module one section that talks about electrical quantities, so think about the topics that were given to you that falls on the module one and see what definitions they might ask you to come up with. All right. So here we have the first definition, volt. When we hear about volt, we know we are talking about voltage, right? So simply put, it's a two-mark question, which means to say you have to actually have good amount of information to get the 2 marks. So we could simply say that volt, right, is the unit of potential difference. And I think by now we know that voltage and potential difference are talking about the same thing. So you get a 1 mark if you were to write that. Then, as it pertains to volt now or voltage in general, right? You could write this information um, pertaining to that says the potential difference or the voltage, potential difference, or you could say PD, right, is when energy of one joule is required, right, to transfer 1 coulomb of charge between 2 points, right, between 2 points, right, and in addition to that, you should also remember the equation for volt or for voltage or potential difference. V is equal to work done divided by Q, where work here is just the energy that is required, right? And Q is the charge. So once you remember this equation here, or even if you state this equation in the whole definition part here, you will get some marks, all right? So as much as you know, if you don't know how to word it, you can write the equations, those kind of stuff to just put, more possibilities of getting some marks here about. So this is what simply potential difference is. And I mean, we said that the unit, uh, volt is the unit of potential difference. So to just add a little bit more information to it, we say that the potential difference is um, when energy of 1 joule, right, is required to transfer a coulomb of charge between 2 points. So imagine that we have a circuit, right, and we have a power source right here, right, and we have some device connected here. Clearly, in order to move the electrons from one point to the next, which are basically the charge, you would need energy to do so. So 1 volt is simply put the amount of energy. It would be 1 joule of energy that would move 1 coulomb of charge. That's what 1 volt is. So when you hear about a 9 volt battery, right? A 9 volt battery is simply saying to us that it has um, uh, 9 joule of energy to move 9 coulomb of charge. So each charge, in a sense, that is inside of the battery will have that amount of potential difference, or 9 volt of energy will be applied to each coulomb of charge, basically to move it throughout the circuit, right? Now, with that being said, since we're talking about coulombs and charge and all that, they asked us to define coulomb, right? As you can imagine, coulomb is the unit, right? Is the base unit for electrical charge. So coulomb, right, is the unit for electrical charge. And with a base unit or SI unit, I mean, because we have to understand is that Coulomb is a SI unit for charge in a sense, Like well, it's a derived unit, so to speak. Let me rephrase that. It's a derived SI unit. So Coulomb is the basic unit or the base unit for electric charge. All right. Now, to define Coulomb, one of the things that we can look back on is the fact that current, right? So let's imagine that current, we know current is the rate of flow of charge, all right? So in order for us to define coulombs, right, which is the same thing as talking about the unit for charge, if we transpose the equation to say Q is equal to I times T. So this is what you would, if you wanted to find the amount of charge, then you would transpose to get IT. So if we want to put a definition to this, to Coulomb, we could say that Coulomb is equal to the amount of charge, right, transported by a constant current. When we say constant current, we mean more like of a direct current in this case, of a constant current of 1 ampere in 1 second. All right, and you get your 1 mark for this, and you get another 1 mark for this. Both of these carries 2 marks. So that would cover that from the standpoint that I know of here. Let me see. I think it's a 3 mark question. It says what? And see its relationship to the elementary physical unit of charge. So if we can recall anything about Millikan's oil dropping experiment, he was the one who found out the charge of an electron, right? And when he did that, he found out that charge is quantized, meaning that there is several units of charge. So with that being said, we can come up with this elementary equation here. Not the equation really, but it's just a way to understand charge. That if you have X number of charge, then that is just N times the number of electrons. I'm seeing something here. I'm not so sure what does this mean. It says, I don't know, you can check it out. It says that 1 coulomb, right, is equal to 6.24 times 10 to the 18th elementary charges. And it's the first time I'm seeing such a thing. I don't know what that speaks to, right? But yeah, I mean, sometimes some of these things are so far fetched that you can't even think. But let's leave that as that. All right. At least you would get at least 2 marks if you were able to define it, the amount of energy transported by constant, of 1 amp to well in 1 second rather, right? Now the question continues, and I mean, once we talk about coulombs, I mean, our charge on a whole, Coulombs law comes into play, yeah, because as you can imagine, whenever you have more than one charges in close proximity, right, then they will experience forces, and I mean, we know that positive charge and negative charge attracts, and opposite charge repels each other, right? And that repulsion that we're talking about is just a force. That attraction that we talk about is just a force. So in this case, they just want us to pretty much identify or to name out all of these variables that are in this equation, Coulomb's law equation. Coulomb's law equation would have stated to us to say that that the force experienced between two charged particles is directly proportional to the product of the charges, right? And inversely proportional to the square of the separation distance between them, right? So all we will need to do is to just identify what the symbols are and possibly state the units. So here we know that force, F is talking about the force, right, between the two charged particles, between the charges. All right, so we can say Q1 and Q2. Unit is newtons. All right, or no, it's a capital N for newtons. So Q1 and Q2, those are simply the point charges rather, and we know that this is in coulombs. Then R, you might see a capital R here. Don't watch that. They can trick you sometimes. So we normally use common R. So that is just simply the distance of separation, or in a sense, the distance between the charges. All right. I mean, sorry for my bad handwriting. I mean, that has always been with me. And the unit here is meters. So always remember to put in everything when they ask about. It's a 5-mark question. Can you imagine you get 5 marks from answering such a simple question once you know the variables? Now, the other variable that we need to know mainly or to identify is epsilon. Epsilon naught. Epsilon naught is simply the electrical permittivity, right? Electrical permittivity of free space, right? And the unit for this is force per meter. Okay, you could derive this unit by just transport. Well, I mean, it can be a little bit of a challenge sometimes if you were to find the units for electrical permittivity of free space, but I mean, it's force divided uh by meter. Now, having said that, you would have scored your 5 marks if you were to properly identify the units and properly identify the variables. Then you get your 5 marks. See? So we're kind of done with that here now. The question goes to say that a 100 micro coulombs, right, and a test charge of negative. So let me start over. So a positive 100 microcoulomb and a test charge of negative 5 microcoulombs are 3 millimeters apart. It says calculate the force between them. They are so they Cape is getting a little bit more easier these days because they give you all of what you need per se. One of the things you must remember, you could write the equation like this. If you see it like this, then you know it's the same thing. So K times Q1 times Q2 divided by R squared. K, simply put, is 1 upon 4 pi epsilon naught, right? When we do this, we get a value of 9 times 10 to the 9. Honestly, I don't remember the unit, but I believe it has a unit, okay? The unit could possibly be um, per Newton. Let me see. Well, what was the unit for electrical permittivity? So this is what? This like Faraday's, you know. By the way, let me correct myself. I think this is Faraday's. So Faraday's per meter. So in this case, because we're dividing epsilon, then the unit would possibly be well, we don't even need to know the unit for this, but let's just say that the unit in this case would be uh, it would be per Faraday's meter, because we're kind of finding the reciprocal per se of the unit of epsilon because it's divided. But if you get a question and you don't know the electrical permittivity, it's at the front of the paper, right? Because they give you a list of constants, so you know that that's going to be 8.85 times 10 to the, I think it's minus 12, all of that, right? So you could find that value at the front of the paper. So having said all of that, you just go ahead and put in all information here related to this question. I mean, we don't have to use the minus sign in the calculation. Reason for leaving out the minus sign just show that the charges will have a repulsive force mainly. But you can use the minus sign inside of there. It's not going to affect the calculation overall. It's just going to tell you that the forces are attractive, so to speak. My bad. It's going to be attractive, right? That's what I meant. It's going to be attractive. Sorry about that. Because you have positive and negative charge, they're going to attract. So that's what that is for. So if we go ahead and put our 9 times 10 to the 9 times the first charge, which is 100. Now, ladies and gentlemen, when you see micro, right, you have to incorporate that in the calculation. 10 to the minus 6, not true? Right? Then we times it by 5 times 10 to the minus 6. Cool? Then we divide this now by r squared. R squared is 3 millimeters. Now, because I'm not a big mathematician, and sometimes if I try to convert 3 millimeters to meters, I might get it incorrect. I know that milli means times 10 to the 3. So all I need to do is to say, okay, 3 times 10 to, well, I should correct myself. I said milli means 3 times 10 to the 3. 3 times 10 to the minus 3. So milli means to the minus 3. So because I have 3 millimeters, right, and this is just a prefix in front of meters, then all I just simply need to do is to just bring back. So rather than writing it in decimals, I can still write it in exponent and get the answer correct. And if I put it in my calculator, then it shouldn't give me any problem. So 3 times 10 to the minus 3 meters is the same thing as saying 3 millimeters. I know it is going to be, if you were to convert it rather to decimal, it's possible would be 0.003 meters. But because sometimes you can make mistake with this, then might as well you just focus on the prefix that is here, right? So because you know the prefix, which is 10 to the minus 3, then you just use that. You just put back that there and put the units for meters, and you can't go wrong really there. So please ensure you watch the units. You have to work everything in SI units, ladies and gentlemen. All right? So at this point now, we're saying 3 times 10 to the minus 3 squared. Now, when I was learning physics, my physics teacher tell me, say, you know what I can do? I can group the powers by themselves, group the coefficients by themselves, to just make the calculation look a little bit more seamlessful or meaningful, or seamless in a sense, or, you know, because sometimes you put in all this in the calculator and you run the risk of getting it incorrect. So what I would do is to say, all right, 9 times 100 times 50, put that by itself. I can work that out. Then now, as it relates to the powers, I just group the powers. So whenever we are multiplying powers, right, the laws of, I believe, indices, right, tells us, or the laws, I don't remember what it's called, or the laws of power. I don't think it's the laws of power, but the law of indices rather, tells us that if we're multiplying powers, we can simply add the powers. You follow me? But before I do that, I'm going to just write it back out, right, as such. Let me correct that. Everybody have a different way of doing their stuff. This is just my way, how I do it sometimes to just kind of prevent me from running into any errors. Then now, let's deal with the denominator. So right here I have 3 squared, right? So everything in the bracket has to be squared. So 3 squared, that's going to give us 9. So the 9 is by itself. As it relates to this now, the exponent, whenever we are squaring an exponent, right, we multiply. It says, you know, power to power like that. We can't square it, but we have to multiply it. So in this case, it's going to be 10 to the minus 6. All right. So this is why your math class is a little bit important. Well, not a little bit, but very important when it comes down to some of these principles and all of that. Now, having said all of this, having worked out all of that, I don't know where my calculator is. Let me see if I can find it. All right. So this is just a way to, if you're having issues with working out some difficult stuff. So we're gonna work out the coefficient part. So 9 times 100 times 5, I get 4,500, right? It's gonna be divided by 9. Now, as it relates to the powers here, we said that power to power, like that, if we're multiplying exponent by exponent, we're gonna add them. So here I have 10 to the 9. Put a bracket right here. Now this is it's a minus. So if I put the plus and put the minus, it will still be a minus. Same thing over here. So I'm plusing the powers. Still will end up be a minus because plus and minus gives you a minus, right? Now we're dividing that now by 10 to the minus 6. Let's just work this apart here. So 10 to the 9 minus 6 minus 6. Then we're going to divide that now by 10 to the minus 6. Let's work out that power. That would be 3 minus 6. So you're going to end up with 10 to the minus 3. Right? Because, I mean, 6 minus, or 9 minus 6, you get 3. Then you subtract that, you get minus 3 right here. Divide that now by 10 to the minus 6. Now, laws of indices tells us that if I have a power in the denominator, a simple way of writing it is to subtract it, right, from the power above. So all I'm doing now is to say 10 to the minus 6, 10 to the minus 3, minus 6. This minus 6 is going to give me plus. Cool? So at the end of the day, we're now saying 10 to the minus 6 plus 6. 10 to the minus 3 plus 6. Alright, sorry about that. So 10 to the minus 3 plus 6. There can be easier ways of doing it, but I mean, if you're running into problems, then you can try this way. But if you don't use this way, don't kill yourself over it, honestly. So now we have this now. Let's divide the 4,500 by 9. We get 500. Cool. Then now we have times 10 to the 3 because, you know, we work out this and we get 10 to the 3. So this, in a sense, is your answer. And to just make it a little bit more colorful, we can say force is equal to 500 kilonewtons. Nothing is wrong with you writing it like that. And that would complete that answer, ladies and gentlemen. Now, the question continues, right, where we're dealing with now a parallel plate capacitor. Now, if you see how the question works, all the questions are connected with each other. So they start off with volt, they start off with coulombs, they start off with Coulombs Law using that force equation. Then they now jump over to capacitors because capacitors have to do with charges, right? So now here we have this question. It says that in the diagram shown in figure 1, electrons are ejected from the lower plate of the parallel plate capacitor with plate separation of 3 millimeters in a vacuum chamber. It says that the ejected electrons have a range of energies and direction. So it said that the electrons are being ejected from the lower plate. Zin, ejected from the lower plate. One other thing you must understand, ladies and gentlemen, is that it's going to require a lot of work. So work is going to be done against the electric field, because what you have to understand, the electric field will be moving from, you know, positive to negative, as you can imagine. Now, we know that positive and negative attract. So this electron here, so right, is being ejected from this angle, from this part. So you will be going against the force of attraction. So, not to confuse you or anything, but that's just look at it and understand what is happening with the charge, right? So because the electron is at the positive, the lower plate, see? And you want to move it to the upper plate at some point. That's what's gonna happen. Then it means that you're gonna basically be doing work against the electric field that is already generated here in the scenario, right? So work is gonna be done uh, on the charge in itself, right? But we could also say that work is being done against the electric field. Now it says for these electrons which are ejected at right angles, right, to the lower plate, it says calculate the maximum initial energy in joule, right? Uh, they can have if none of them reaches the upper plate, which has a potential difference of minus 3 volts with respect to the lower plate. This is very, it's almost, when I look back at this question, what comes to mind is talking about what we call the stopping potential in photoelectric effects, right? Not technically the same thing, but it kind of brings that to my memory because when you're doing the whole photoelectric effect question and all of that, and that electron was ejected from the metal target, you would want to find the maximum kinetic energy, right? And to find the maximum kinetic energy, it would be the energy that is coming from the power source that would literally stop the electron from reaching to the upper plate. Because what you'll understand here, ladies and gentlemen, is that if you bring the electrons all the way up to that plate, then chances are it's going to be reflected or deflected in a sense because negative to negative they're going to repel each other. So what they want is for us to find out that maximum energy, right? That will prevent or prevent the electrons from reaching the upper plate. In essence, they will reach close to the upper plate, but not technically. It's technically at the upper plate, but technically not at the upper plate. A very tricky scenario, right? So it's just before you reach that. So you want to find out how much maximum kinetic energy those electrons will have, and in order for us to do that, we have to factor in certain things here. So one of the things we must understand, we must know the distance of separation. We know that this thing has a cluster. This is going to be -3. This is going to be +3. So you know the potential difference that is across the plate, which means to say we could actually find the electric field if we wanted to find that at some point. But let's see what method we're going to use here to find out that amount of energy. Remember now that to move an electron from one point to another point, that is talking about a potential difference, right? And we know potential difference to say energy divided by E. Remember now, you're doing work again on the charge to move it from one point to another. See? Now, to the potential that you're trying to move the charge to is going to be the 3 volts. We know that the charge of an electron is 1.6 or negative 1.6 times 10 to the minus 19. So if we were to really, manipulate this, we could then find out the maximum amount of energy that it would require to move the electron from, positive plate to the negative plate technically, right? So that's what we're going to do here. So we want to find the work. The work is equal to V times Q. So V is 3, right? And the charge of an electron is 1.6 times 10 to the minus 19. And with that being said, we can come up with the answer. If we go ahead and multiply 3 times 1.6, we get 4.8 times 10 to the minus 19 joules. And we know that the unit for this is joules. So that's simply put what you're getting. So let me tell you what you're getting marks for. 1, you're getting marks for the formula. So for all of those lazy persons who don't like to write their formula at the first instant, you're getting marks for that. 2, you're getting marks for the substitution. When we say substitution, we're talking about you subbing in the correct values here, right? And in a sense, could also be like talking about the transposition and all that to some degree. Then you're getting marked for the answer. So when you go on the exam, you see, please, me I beg you, do everything according to how it's supposed to be done, right? So you can get all of your marks. Because I mean, this is so easy. So you're getting marks with just subbing the values and subbing them correctly. And you work out that you get 1 mark. One, two, three, 3 marks. Almost finished the exam already. Now the question goes to say determine the maximum initial velocity of the electron. So one of the things you must remember now, this equation can never lose you. A while ago we calculate the maximum energy, kinetic energy that the electron are gonna have. So if we find the maximum kinetic energy, then that means to say if we use this equation that says half mv squared, then it means that we can transpose to find the maximum voltage. My bad, not voltage, but velocity rather. So just remember these equations in the back of your head, right? To say that the maximum kinetic energy equals to half mv squared, right? So having said this, we can now go ahead and transpose for v, right? So by the transposition, and by the way, this is a 3 mark question. So you're getting 1 mark for the formula. Then to just transpose it correctly, you know what I mean? So let's just transpose it first. We'll put in the values. So this is a half. So this 2 is going to come over here. So we have kinetic energy multiplied by 2 equal to mv squared. Now we want to get rid of the m. So you must also know how to transpose correctly, guys. When you're transposing, you move the furthest thing away from what you're trying to find. So in this case, the half was in my way. So I move it out of the way, go over that side. Then the m is now in my way, so I need to divide both sides by m. Right? Cancel m on one side, so I'm now left with 2ke over m equal to v squared. I want to find v squared. So if I want to find v squared, then I find, go ahead, so watch. Yeah, record something. What I say? Wow, like, remember say unit 1 hour next week Monday, not true? Unit 2. Honestly, I don't know. Right now, I'm just working out a paper for them, basically. So when I send it out, not with them, but when I post this, I'm gonna post it on my YouTube page so they can watch it and see how it work out. Yeah, well, me not, well, same thing. Me I gotta do. Me I gotta just work out the papers and they can have it like that. Because I mean, yeah, but I mean, if we can meet with them, still in nothing wrong with that. But for unit 2, mm-hmm. But Mr. Walsh, remember say the exam now, I'm on there now. Soon, 28th exam. Yeah, the exam is Monday. So it would be at school. That's what you're saying. Okay, okay, all right. I'll let you know. Hmm. Yeah, so we're just gonna find the square root now of this, right? Square root of both sides. We know the square root and the square cancels out. So we just need to do it on that side. So at the end of the day, we say now that v, which is the velocity, is equal to the square root of 2ke divided by m. The mass of an electron here is always given to you, right? So all we just need to do now is just put in the value. So 2 times the value that we got for the kinetic energy, which is 4 times 4.8 times 10 to the minus 19 divided by 9.11 times 10 to the minus 31. That is basically your uh, the mass of the electron. So once you finish work out that and you do everything properly, you're supposed to get a value of 1.03 times 10 to the positive 6 meters per second. That's what you're getting the 3 marks for. So that would complete that, ladies and gentlemen. All right. Now the question continues. Question says, it's a 5 mark question now, See? It says calculate the acceleration of the electron in, the question that we have been working on so far, right? Acceleration. So one of the things you must know, ladies and gentlemen, that the thing is in a vacuum uh, thing, because when you look back at the question, it says that it's in a vacuum chamber. So it means to say that no gravity is affecting this thing, right? The acceleration is not going to be caused by gravity, so it can't be 9.8 meters per second squared. It can't be that. So in order for us to find this now, it's going to bring back a lot of things to our memory. What I think that is going to ask us to, it's going to require for us to bring back is this thing here. We want to find the acceleration. The equation we're going to really use is this equation that says force is equal to mass times acceleration, right? Newton's second law, right? However, in order for us to find out the force that is being experienced on the electron, we now have to think back about the whole electric field, right? Because as you can imagine, if an electron is going to experience a force, then it is going to be as a result of the electric field, right? So an electric field is just that region through which a charged particle experience a force. So because we are dealing with a parallel plate, they gave us the distance of separation, right? D. They gave us V. Anytime we're dealing with a parallel plate, ladies and gentlemen, we know that your electric field is equal to V upon D, right? V upon D. So we can go ahead and find that value. Now, as it pertains now to the force, right? We said that electric field is equal to the force experienced per unit charge, right? So having said that, we can now make a transposition for E in this equation and transpose for the force, or we could say force is equal to E times Q. So force is equal to V upon D times Q. We know we're dealing with an electron, so we can now go in this equation and say, all right, V times Q upon D, right, divided by the mass is equal to A. All right, so all of this, you're getting marks for all of this, ladies and gentlemen. So please don't neglect the 5 marks. And I tell you the honest truth. So the volt, as we would have found out already, is 3 volts. Charge of the electron 1.6 times 10 to the minus 19. And then now D, which is technically the separation of distance, I believe that was what, 3 times 10 to the minus, let me just go back and look because I don't want to say the wrong thing. Yes, so 3 times 10 to the minus 3, right? Times the mass now, which is what? Technically, yes, so the mass of the electron would be 9.11 times 10 to the minus 31, right? This is going to equal to A, as you can imagine. So once you work out this, then you should get a value, right, of 1.8 times 10 to the 14 meters per second squared as your acceleration. That's the value that we're looking to get right here. So, right, that's the value we're looking to get. So let me tell you what you're getting marks for, right? You're getting marks for this equation here. So you're getting 2 marks for this equation, right? You're getting 1 mark for the answer, or 1 mark for this substitution here. So you're getting 1 mark for this. You're getting 1 mark for this formula. So that's how the 5 marks is added up. 1, 2, 3 plus 2, 4 plus 1, 5. All right. That is the marks, ladies and gentlemen. Now the question continues, and I must say that for this part, you would have to use a protractor to find out some information as it pertains to. It says that the graph in Figure 2 shows the trajectory of one electron which is ejected at an angle theta to the lower plate. It says each large large square rather, um, with board with black with block border has a side of zero point 0.5 millimeters. So in a sense, I'm assuming that this is what they're saying, that this is 0.5 millimeters. 0.5, 1, 1.5, 2, 2.53. That's what they're saying. So they say draw a tangent, right, to the graph and measure the angle of ejection. So you have to the electron that eject from. The eject from here. So you're going to draw a tangent. If one line go up like this, right? Then once you draw the tangent now, you have to have a protractor. So please go in the exam with protractor. I can't tell you if you're going to get a protractor question, but go in the exam with a protractor. Then you're going to put the protractor right here, and you're going to get some type of angles. All right. Now, as it relates to those angles that you should be getting angles. Let me see something here. There might be another part to that question there. I might left it out. I might have left it out. I think I left it out by accident. However, so I think the other part of the question, if my memory serves me well, if I left it out. I don't think I left it out, you know. Did I leave it out? No, I didn't leave it out. That is a different way of working this out. All right, never mind. All right, cool. So once you get that, now the range of angles that you should be getting, right, is, the angle of ejection really and truly is supposed to be 30 degrees, right? That's the angle you're supposed to be getting, right? Once you draw the line correctly, see what I mean? And I must let you know that for the tangent, the line must touch it at one point, like in one place the line is supposed to touch it. So let's imagine that this is where the tangent is supposed to be, for argument's sake. I'm just doing this. Once you draw the lines in, it's supposed to just brush against the curve one time. This is not done correctly, but it must just brush it to one place. So right here, so you basically have that. So you want to get your ruler and you put it somewhere, and chances are it might just touch it right here. So I can't draw it on the computer like that, but it's going to just brush it one point. But you have to now make sure so the line come all the way, possibly down to this side also, so that you can now measure the angle in between here. So it should be the angle of ejection. Then the question says, read off the maximum height reached from the lower plate. So all you need to do, they give you the information to say this is 0.5, 0.5 again. So all you know is basically a graph question, So we have basically 0.1 here. So then you go in between and you read these smaller boxes now. And I must let you know, if you're going up by 0.5, cool? Then it means that these small boxes in between here. So this box would represent 0.01, 0.02, 0.03. My bad. Let me correct myself. That's not correct. So this would be 0.1 rather. 0.1. So this would be 0.1, 0.2, 0.3. So we're now reading up all the way up to this point here. So that's the maximum height, right, that the electron would have attained. So we know that this is what, 0.5. This is what, 1. Then we have 1, 2. I would say that the answer would be this, right, for the maximum height. Okay, yes, millimeters, and of course millimeters. If you say 1.3 millimeters, then you can get the mark for that. All right. Now it says read off the graph again to the plate before being reabsorbed. So it says read of the distance traveled um, to the plate before being reabsorbed. So that is just you counting the boxes here again to find out how the distance basically that horizontal distance. So let's count how many boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what we're doing essentially is saying 14, right, multiplied by zero point 0.5. So that's going to give us 7 millimeters. All right. It's going to give us 7 millimeters. So that this is a 1 point millimeters. This is now 7 millimeters. You just count the boxes, guys, and finding out how much that box represents. All right, we're moving on now. I really want to go through this part. I mean, yeah. So here we have an LDR. I mean, explain briefly what is an LDR. LDR simply put is a light dependent resistor, or light dependent resistor work. It simply works when light is shone on it, right? So it's a sensing device, as you can imagine. Um, so it's now going to react with external factors, so such as light. So once light shines on the LDR, um, it's now the resistance is going to change. So possibly, uh, let me see if I find something here to just let it be a little bit more concrete in terms of. So as you can imagine, LDR is a resistor, right? So once the intensity of light changes, the resistance changes. I want to say that the resistance is going to decrease with an increase in light intensity. So the more light you have being shone on the LDR, it means that more current will be able to flow through the LDR, thus reducing the resistance. Because for the mere fact that your resistance is decreasing, then it now allows more current to flow through the um through the LDR, right? So it's made up of a semiconductor material, as you can imagine. It's what we call an input transducer, right? It's an input transducer. Um, it's usually made from light photosensitive materials. Okay, so that's technically what you ought to say about this. It's a transducer, but it's a more of an input thing because it is taking some external factor, changing the resistance, right, which will now have an impact on something else, right? So it will now tell the light bulb to turn on, tell something. So when you think about like a street light, right? A street light works with this scenario, right? Those things that you see that on the light pole, that blue thing, it is technically an LDR basically, but the thing is the circuit is somewhat reversed in a sense because as you can imagine in the daytime the light is off. So I believe that they would have just turned around the polarity of the the LED so that it doesn't allow current to flow through it at that point. But as soon as the resistance is high, then it allows current to flow through it, and all sort of crazy stuff taking place here, right? But it's really an LDR that is being worked here, because as you can imagine, during the day, the more light intensity, resistance is going to decrease, more current is going to flow. But that doesn't tell you that it's going to turn on the light. It's based on how the circuit is designed, but you're still using an LDR. So that's one application of that. So here we have a circuit now. This is a Wheatstone bridge, as you can imagine, with different resistors. The whole purpose of a Wheatstone bridge from time to time uh, is to find out the resistance of a particular resistor, that kind of thing, right? So in this case, we have four resistors. In generally, in all cases, you will have four resistors connected in a bridge circuit. One other thing you must remember about a Wheatstone bridge is that there will always be a galvanometer in the center here. This galvanometer is here to enable the circuit to be balanced, meaning that you have equal amount of voltage going on one side and equal number of voltage going on the other side. Uh, so generally speaking, the galvanometer has to be at zero, right, in order for the Wheatstone bridge to be balanced, right? So no current should be flowing through the galvanometer. When no current flows through the galvanometer, it means that the voltage on this side is equal to the voltage on the other side. You can rearrange this circuit to just show you a little bit more as to what is happening here. So imagine that I redraw the circuit, right? Like this. So I haven't done anything different. All I'm doing is just redrawing the circuit so that it looks like a parallel circuit. Because in order for us to understand everything about these circuits, right? And by the way, this arrow looking thing that you're looking at here is just simply a variable resistor, right? Nothing fancy, nothing too complicated. It's just telling that you can vary that resistance, which in turn is going to cause some variation. This is the symbol for the LDR, just a circle around it with a resistor in the middle. So this, what you're looking at here is the same thing, you know, right? This is the same thing. Let's put back our galvanometer here. So sorry for the ugly handwriting, but you know, that's kind of help just work with it for now. Put back our power source over here. So in essence now, what you're looking at technically, ladies and gentlemen, is that you have a parallel circuit. Remember now, once the bridge circuit is balanced, then it means that no current flows through here. So you can take this out of the circuit technically because it's balanced. So no current is going to flow through this. So it means now that you have a complete parallel circuit, which means that in parallel circuit, we know that voltage remains, or we say now, remains constant, right? So voltage is going to remain constant and current is going to be divided. We know that already. So we're going to use that basis now to help us with understanding something here. They want us to show that the bridge is balanced when that is equal to that. So all we're going to do here is to basically derive the equation in a sense. I mean, which I don't remember how much marks is, I don't remember how much marks is value, but it can be a lot of things to think about. But what we're simply doing here, we're going to just use the whole knowledge of potential divider, right? Because remember we said that the voltage over here, so, right, is equal to the voltage over here, so. See? So this is how we're gonna take it now, right? We're gonna do this. We're going to find the voltage across R3. That's what we want to find, right? So if we want to find the voltage across R3 using the potential divider formula, right? It tells us that V3 is equal to R3 times our voltage that came from the power source divided by the sum of the resistance, which is so the sum of the resistance here is this resistor that we're talking about, these two resistors, because these are in series with each other. So R3 plus RL. Then now, moving on to the other side. Sorry about that. Moving on to the other side. This side, we want to find the voltage in R2. So we have two resistors connected in series, R1 and R2. Remember we say now that the voltage in R2 will be the same voltage in R1. That's what we're just getting at. So R2, want to find the voltage in that, so we use the potential divider formula again to say that V2 is equal to R2 times V, which is the voltage of the power supply, divided by the sum, which is R2 plus R1. Now, because we said that the voltage is the same in parallel circuits, it means that the same voltage over here, so will be the same voltage over here. So we're going to equate both equations. So technically speaking, we're saying that V2 is equal to V3. If V2 is equal to V3, then we can say R2 times V divided by R2 plus R1 equal to R3 times V divided by R3 plus R2. Now, V and V are common on both sides. That's the same voltage coming from the power supply. They're common. So now what we're left with is this equation right here. See, so all we're going to do now, let me just reevaluate something here. So this is RL, by the way. It's not R2, RL. RL, yes. So what we want now is to simplify this, right? We just need to simplify it. So in order for us to do that, we are going to let me see what I'm going to do here. What would be the best thing to do? Okay, I believe this is the better thing to do at this point. Let me see. All right, give me a second here. All right, so we're going to transpose the equation, right? We're going to bring this across. We're going to bring this across. So we have R2 multiplied by R3 plus RL equal to R3 multiplied by R3, right? R2 rather, R2 plus R1. So we're just going to expand these things. So we have R2 times R3 plus R2 times RL equal to R3 times R2 plus R3 times R1. So one of the things now you're going to realize is that this is common over here, so this is common over here. So if we were to even transpose the equation, you would have realized they would cancel out, right? If we were to subtract them, it would cancel out. So what we're really left with now is R2 times RL is equal to R3 upon R1. They want us to find RL. RL is going to be equal to R3 times R1 divided by R2. So that will give you your marks. I don't know how much mark is value. Let me just check and tell you. But you must know how to do these things. It's possibly a lot of marks. How much mark is? Yeah, good amount of marks, you know. 1, 2, 3, 4, 5, 6, 7, 8, 9. No, I don't know if it's so much, but it's quite a lot, right? Quite a lot of marks. I think it's 5 marks. You could have gotten it. You could have done it a little bit easier, but this is technically the easier. Well, not the easier way, but this is the fundamental way of getting this equation, basically. So once you do that, you get that mark. Uh, so I think I'm going to pause the video here, right? And then I'll continue it with the next part of the question and all of that type of stuff, right? So hope you enjoy. I hope this makes sense to you. If you have any comments, just let me know.